Hello students, in this video we'll begin our discussion with orthonormal bases in Rn. Let's let phi 1 through phi n be an orthonormal basis in Rn. Okay, so what does this mean? This means several things. That the set, it has to be a basis itself, right? So in other words, 1 and 2 is that the span of this set, the span of phi 1 through phi n is Rn. And the set is linearly independent. Phi 1 through phi n is linearly independent. But now we're specifying, of course, I've just recapped what a basis is, right? Now what does orthonormal mean? This is where the interesting part comes in. I'm going to assume 3 that phi I dot phi j is delta ij. And what is delta ij? It's the Kronecker symbol, right? And now, of course, I can be really picky about this and say, do I have two covariant indices or two contravariant indices, or is it a mixed tensor, covariant, contravariant? We'll get to those issues later. I'm just going to sort of formally define this and not worry about covariant, contravariant, because we haven't discussed that yet. We'll discuss that later on in the course, where I might have to change the indices because I might want this to be a dual basis, okay? So we'll talk about those issues later. This is going to be what? This is going to be 1 if I is equal to j, and 0 if I is not equal to j. In other words, if you dot one of the phi's with itself, like phi 3 dot phi 3 is 1, but phi 3 dot phi 4 is equal to 0. Phi 10 dot phi million is equal to 0, right? So all the ones where the indices do not match are 0, and the ones where the indices match, the dot product is equal to 1 in that case. Great, okay? So what can we say about this orthonormal basis? Of course, the classic basis, the classic orthonormal basis of Rn is just the standard basis, right? It's just E1 hat through En hat, right? But of course, there are many others, right? Any basically orthogonal matrix I do times this basis will give me an orthogonal set, okay? And so what are the basic properties of these? So there's several very important theorems about this. Here's the first proposition. Prop is that, in fact, we can sort of reduce the requirements over here, right? So the first proposition is that if phi 1 through phi n is orthonormal, then it's going to be a basis of Rn, right? In other words, I didn't need to say basis over here, right? And so here's the proof, right? So they're linearly independent. So if we suppose that lambda 1, phi 1, plus lambda n, phi n, is equal to the 0 vector. And I'm going to take this equation over here and we're going to dot this with phi I for any fixed I, right? So if we dot this equation with phi I, what's going to happen over here? Well, let's look carefully and see what we get. We're going to have phi I dot lambda 1 phi 1 plus lambda n phi n. So when I distribute this dot product, we're going to have all these dots. It's going to be lambda 1 phi 1 dot phi n. That's phi 1 dot that's phi I dot phi I, right? So phi I dot phi I. So that's going to be a phi lambda 1 phi I dot phi 1 plus lambda 2 phi I dot phi 2 all the way down to lambda I phi I dot phi I all the way down to lambda n phi I dot phi n, and that's just going to be 0 because when you dot with 0 you get nothing. The only one of these terms that survives is the phi I with phi I. So this term over here is the only term that survives this dot product, and this tells me that lambda I, because phi I dot phi I is equal to 1, so this lambda I is equal to 0, and that shows that all the lambda I are equal to 0. So the set is linearly independent. So this set is linearly independent, and there are n linearly independent things is linearly independent. And there's n of them. and that implies it's a basis of Rn since the dimension of Rn is n. Okay, great. That's the first result we want to prove. The second result we want to prove is we want to figure out how to, so it's linearly independent, and now we actually extract these coefficients. So the same mechanism allows me to extract the coefficients, right? So here's the next proposition. This is the Fourier proposition. So proposition for any vector v in Rn, then v is equal to what? Then v is equal to, I force of habit to do the inner product notation. It's going to be a v dot phi 1 under the same assumptions that this is a what? I'm using the same assumptions that this is an orthonormal set, right? V dot phi 1 plus v dot phi n, compact, I can write this as the sum, j goes from 1 up to n, of v dot phi j, those are the coefficients, phi j. Okay, so these coefficients over here are called the Fourier coefficients with respect to this basis. These are the Fourier coefficients with respect to the basis of phi 1 through phi n. Okay? Of course, the proof of this is exactly the same as before, right? So let's prove it. So proof, we write v as lambda 1 phi 1 plus lambda n phi n. And the same reasoning over here, I'm going to take v dot phi I. Well, v dot phi I is phi I dot lambda 1 phi 1 plus all the way down to lambda I phi I all the way down to lambda n phi n, right? And when I dot phi I with any of the things that aren't this one right here, by the orthogonality, all those zero out. So we're left with what? We're left with just lambda I phi dot phi I, which is just lambda I. So what is lambda I? Lambda I is v dot phi I, and that gives us our proof of this Fourier decomposition over here. So this is, in some sense, a finite Fourier series. Right, and the key fact over here is that we can really think of this, the identity, we've basically written this as a whole bunch of projections, right? So this sum over here is a whole bunch, is a finite sum of projections, right? So each of these are projection operators added together. So it gives us sort of a tinker-toy version of the spectral theorem for finite self-adjoint operators, in this case for these symmetric operators. So we're sort of getting towards the idea of how we prove the spectral theorem. We want to basically break it into orthogonal pieces in some sense, or at least for self-adjoint operators, I want to break it into orthogonal pieces, and I want to reduce that and use induction. So this gives us a basis for idea for how we're going to approach the spectral theorem for self-adjoint operators. Thank you very much.